everybody. Welcome to the conceptual design of a horizontal takeoff, horizontal landing, single-stage orbit space plane. We are Zenith Aerospace, and I am Bernd Talari, the chief engineer for this project. Getting straight into our mission parameters. We, along with two other teams, are tasked with designing a single-stage orbit vehicle with 3 different configurations. We will be doing the horizontal takeoff, horizontal landing, Apex with the vertical takeoff, vertical landing, and then Saturn with the vertical takeoff, horizontal landing. The purpose of studying these 3 different configurations is to find the most optimal configuration for single-stage orbit, because this is the next level of technology for space planes. We all have the same mission details, which is to design a single-stage orbit vehicle. We are to take off and land at Cape Canaveral while holding a 30 kilopound and 50 kilopound payload. We are to trade packs count with payload weight, and we're to generate a solution space with applicable vehicles on there, along with a 3D print of our solution space and then a 3D print of our base designs. They're going to be here on the board and the side if you want to look at them. Getting straight into our history and introduction, these 4 planes are pretty important for our vehicle because they directly influence the development of our vehicle. Space Shuttle is a good vehicle to note because this is the first reusable lifting re-entry vehicle. It uses a compound delta wing, a blended wing lifting body style, and this was used by NASA until it was retired. The X-30 is the next aircraft that was supposed to succeed the Space Shuttle. It was another single-stage orbit vehicle with another compound delta wing, lifting body, and a hypersonic air-breathing engine. The X-43A is a good plane to mention. This is not a space plane, but it is a good aircraft to mention because it uses a stretch jet technology for the rocket, or for the engine, and that will directly influence the development of our vehicle. And then the Radian one is a good vehicle to mention because it is a currently developing vehicle that is single-stage orbit and horizontal takeoff and horizontal landing. However, it does use assisted takeoff. To design vehicles like this, we can generally split into 3 different phases: conceptual design, preliminary design, and detailed design. Conceptual design is essentially taking our mission requirements, looking at all the different concepts that we can use for the mission requirements, and putting them all together and integrating them into a single vehicle concept. We can then bring that into preliminary design, where we flesh out this vehicle, understand what really is required to make this vehicle, and then detailed design is then getting into the nitty-gritty details, doing wind tunnel tests, understanding how we're going to transition to manufacturing. I want to note that conceptual design is the most important one here. Aerospace vehicles require a good base to ensure that the vehicle can make its way through the design phase. And if you don't have a good idea of what the ideas going into the vehicle are, then it's going to be extremely inefficient and cost inefficient for the development program to go through this. To do conceptual design, we can split into 4 different phases: project initiation, parametric sizing, configuration layout, and configuration evaluation. Project initiation is essentially generating a list of lift, thrust, volume, and control components that we can then use into our gross geometry of the vehicle to then bring into parametric sizing, where we then size it using a parametric study to understand how these technologies will work during different analyses. We then bring that into configuration layout, where we then understand how the vehicle is going to look when we lay out the vehicle with different kinds of components and all the different surfaces, and then we then evaluate it in configuration evaluation. And we then bring it back to configuration layout if we need to review it, or we have our final vehicle concept. I want to note that this entire phase, all the 4 different phases, are built on literature research. Literature research is the core of everything we do, and without literature research, we don't have a vehicle. For us, we collect the resources and categorize it. We then gather what's required and what we need from each literature, and then we identify and select methods that we need. And this process is extremely important for us to do, because without this, the vehicle you wouldn't know what technologies are available, and the vehicle wouldn't be built on a base of already seen knowledge. This is a team that's conducting the research. I'm the chief engineer. VFAM over here is our co-chief engineer. This is a little bit of our timeline. We're kind of at the tail end of that. Every week we have a weekly meeting with our team to discuss how the project is going, how progress is going, and everything within it. It's important that we have a good organization within a team, because without organization, we can't be a team.
They are very busy.
We are very busy. Project initiation, getting straight into it, we are essentially taking a structured approach to understand how to develop feasible concepts that we can then output to parametric sizing. We have a clear objective and clear purpose for the project, and we're using a systematic approach to identify potential designs that we can then use to size and parametric sizing. And it's important that we do this process because we want to be efficient, focused, and aligned with our mission goals, and we want to pinpoint the specific technologies that we will be using in parametric sizing. This is the process that we did. It's a synthesis-based MDA. We use 5 different phases in this process: input, research, analysis, concept selection, then output, and this allows us to make a feasible vehicle. The big idea of this MDA is essentially to take our mission requirements, use relevant vehicles and decompose them into our 4 different components, along with finding other available components from research to then combine that into a feasible vehicle concept that we can use in parametric sizing. First up is TMP.
Hello everybody, my name is Scott Booth. I'm the lead for trajectory and performance. And for project initiation, we were tasked with finding the flight regimes that the vehicle was being required to fly through, which performance requirements were the most important in order to essentially what limits the vehicle. We did this by performing a comprehensive literature review of prior vehicles and prior feasibility studies, and to determine similarities in the trajectories between them. This allowed us to find the values and the parameters that were most important for the successful mission. So you can see we went through 6 different flight phases: takeoff, air-breathing climb, and onboard oxidizer climb, orbital maneuvers, re-entry descent, and landing. Each one has its own unique challenges and requirements that must be completed by one vehicle. You can see generally there are several forces and several moments that act on an aircraft that are very difficult to model, requiring complex state matrices and complex partial differential calculus. This is impossible to do this early in the design process because there is not a way to get that information. Therefore, we need to utilize reduced order models that take those complex systems and reduce them down to something that can be more easily evaluated early in the design process when limited information is known. Next slide.
The objective for geometry and PI is to find the differences of different cross-section designs by identifying the pros and cons of different cross-section, and to determine the rationale behind different volume distributions. The purpose is to conduct research of similar vehicles to find the most feasible fuselage characteristics, which will be sent to synthesis to be integrated with our initial concept vehicle. Next slide. The methodology is executed by conducting analysis of the similar vehicles' fuselage cross-sections and the volume distributions, and we rank based on our mission requirements and how feasible they are integrating with our concept vehicle. Next slide.
Good afternoon, everyone. My name is Aaron Keeter, and I'm the Aerodynamics and Aerothermodynamics lead at Zenith Aerospace. In project initiation, Aerodynamics was responsible for investigating the lift generation components of our concept vehicle. Due to our mission profile, this posed challenges since both low-speed and high-speed flight vehicle configurations are vastly different. So what we did was we optimized for high-speed flight regimes while still having just enough to take off and land. Next slide. These are the lift generation components that we investigated alongside sampled concept vehicles. For our body configuration, we went with a lifting body since this provided the highest amount of high-speed performance. For wings, we went with double delta because this bridges the gap between low-speed and high-speed flight optimization. Next, we went with a low wing placement to reduce our interference to drag and provide re-entry characteristics. And lastly, we originally went with a rear engine placement to avoid plume expansion in the belly of the vehicle. Next slide.
Hi, everybody. My name is Tom Lee. I'm the stability control lead. During the project initiation phase, the stability control discipline was in charge of defining all components required to satisfy all FAR 25 requirements. Next slide, please. Here are the components that were chosen. These were chosen based on multidisciplinary analysis. Next slide, please. And these were chosen using a component vehicle database from historical vehicles, and this is how they shape the final design.
During project initiation, propulsion's main job is to determine thrust generators, and we did this by performing literature research across combined cycle engines, and we determined how thrust was generated, placement of the engines, and engine performance. We also traded hydrogen and hydrocarbon fuels. You can see our organization right over here. Next slide. You can see we researched past engines, how they operate, and which ones we chose. Next slide. We analyzed mission requirements and executed our methodologies to determine that the turbine combined cycle engine, the rocket combined cycle engine, and the aero augmented rockets were the main categories of engines that would be feasible. Next slide. We determined that the RBCC engine was the best because it was lighter and less complex, and we could easily integrate it into our designs. You can see that it operates in augmented rocket mode, ramjet mode, scramjet mode, and rocket mode again. Next slide.
All right. Hello, everyone. My name is Sanjay Dipal. I am the Weights and Balance, Structures, and Materials Lead. And our project initiation weights and structures main objective is to establish the internal components research as well as the different TPS and the landing gear configuration. And this will be all done in preparation for the later phase in CL. The most viable components that we establish would be then given to synthesis to start as an initial design point. Next slide, please. So here are different vehicles listed for their different mission profiles, whether low Earth orbit, horizontal takeoff, vertical landing, and everything, and different type of materials, internal structures, as well as the landing gear configuration. Next. So in terms of landing gear configuration, it's very important to understand that for a horizontal takeoff, horizontal landing, for a single stage orbit, it is extremely heavy. So the different types of landing gear would be the most optimal one would be the tricycle or a quadricycle configuration for it to withstand all that load upon takeoff. And then there are different types of ribbon spar configuration as well as materials, TPS that could be composite or newer materials, and the systems that are environmental control systems that would need to be considered during low Earth orbit. Next slide. And here is the chosen rankings for all of these systems. Thank you. Next.
Good afternoon. My name is John Batitang, and I'm the Cost and Safety Lead for Zenith Aerospace. For cost and safety, our main objective is to determine the potential markets as well as the safety regulations that are imposed on our space plane. This is done by conducting a conductive literature research and compiling this database and outputting what we have to the various disciplines that need them. Next slide.
There are literature research. There was 4 markets: commercial sci operations, research institution, space tourism, and military defense. Within those markets, the vehicle must follow from 14 CFR Chapter 3 and FAR 25 regulations. And with those information that discuss markets sent to synthesis, information that discuss system requirements and safety sent to weight and structures, information about sizing the vehicle based on FAR 25 sent to texture and performance, and information about stability and control sent to stability and control. Next slide. Through our research, we found, and these were our results. And through our literature research, there were 2 main questions that we kept in mind. Who will benefit using our vehicle, and how do we keep our vehicle safe? Next slide.
Hello, I'm Lee Pham, and I'm the co-chief of Zenith Aerospace. And from the compiled data of the involved disciplines, synthesis will develop a process to analyze and select the best new concept for the mission. This analysis includes asking different combinations of components to identify how the components interact with one another. And through this analysis, the achievability of the vehicle concept, given the current and future technologies, as well as safety compliance, will be determined. Next, please. The distinct feature of the following concept of vehicle models in this design phase was implemented 4 key components, which is lift, thrust, and volume, and control surfaces. The 4 selected are the force of lifting body, compound delta wing, and low wing placement. Next, please. Which from the analyses, I'm sorry. Oh, sorry. Go ahead.
All right, so with that final concept vehicle that we made in project initiation, we then moved into parametric sizing. And in parametric sizing, one of the big things that we have to look at through literature research is the different legacy sizing methodologies that are available to our hands. Some of these are Lofton, Nikolai, and Roskin. These are all weight-based sizing methodologies that either are iterative or non-iterative. And these were looked at, but not feasible for our vehicle. And so the feasible sizing methodology that we chose was ABD sizing, which is a derivative of hypersonic convergence. The main parameter that is going to be iterated through this methodology is tau, which is slenderness ratio. Tau essentially tells us how much volume and how slender the vehicle is going to be, and this allows us to integrate volume along with weight into our convergence. And the reason why we went with ABD sizing over hypersonic convergence is because it allows us as vehicle designers to iterate through more vehicle design variables along with putting the constraint analysis within the iteration. This is the process and MDA that we use to to conduct parametric sizing. And the big idea for this is to take that vehicle concept, use mission requirements to then identify key sizing parameters and logic to then iterate through that, generate a solution space, and then we can select a design point from that solution space. The first analysis that we're doing is geometry.
The objective of geometry is to establish a KW versus tau relationship. This allows us to size and shape the vehicle for the convergence process. Next slide, please. Using the initial configuration from PI, it was then iterated through different sizes, such as the length and planform area, while holding aspect ratio and slenderness constant. Through the iterated models, the KW and tau values were evaluated. Next slide, please. Using the evaluated data, a MATLAB curve fitter tool was used to establish the KW versus tau relationship. This was providing to synthesis and Aero for their analysis.
The microphones.
All right, so for parametric sizing, weights and structure's main objective is to determine the structural index as well as the different weights and volume parameters that go into the weight and volume budget for the synthesis discipline for their hypersonic convergence project as well. So, next slide. In order to do this, we had to conduct literature research, and the main one that we looked into was the trans-atmospheric launcher sizing by Paul Says, which gives us pure empirical data on past vehicles and the ranges for all of these parameters. And then through our analysis, we could determine the fixed systems weight and the fixed volume weight as well. Next slide. And we would then conduct a sensitivity analysis working with the synthesis team to determine the most optimal takeoff gross weight, which we're trying to lower to improve cost and performance as well. And these are our results for weight and volume parameters. In conclusion, they all showed a positive correlation, but it varied in different magnitude. And then we later learned that through the iterative process that we were very optimistic in these volume parameters, which we had to reconverge to allow for volume allocations. Thank you.
So in parametric sizing, the primary goal regarding structures is finding a value for structural index. So this parameter basically describes how the structural weight is divided onto the area of the vehicle. And typically we want this value to be lower. The process began by taking the surface design temp chart provided by Coleman and then taking the value for typical SSTO vehicles. This was then reduced by about 18% to account for use of composites, since they significantly lower the structural weight. Next slide, please.
In parametric sizing, aerodynamics was responsible for determining the aerodynamic characteristics of the concept vehicle and to provide an initial airfoil shape for the wing, canard, and detail. The way that we went about this is we went with the, we used empirical data to determine the airfoil shape for all three of those, and the aerodynamic characteristics, we went to trajectory and performance for their thrust ratio analysis and their trajectory simulation. The airfoil shape went to geometry for their initial configuration. Next slide. For aerodynamic characteristics, we calculated the coefficient of lift, drag, and the lift to drag ratio. The resource that we found uses the Coran model with adjustments for the X43 body configuration. This configuration is very close to ours, so it's verified very, very well. say the least. The two inputs that this method requires is Mach number. So from truck performance, we got a range for Mach number. And for tau, we can see in the bottom how that change in tau would increase the vehicle's trajectory. Next slide. These are the results that we got for our aero execution. The important part here is that as you increase in Mach number, your L over D did go up. However, our coefficient of lift and drag did decrease. Next slide.
So in parametric sizing, propulsion is tasked with finding thrust over weight and engine volume coefficient. This will be given to synthesis so they could allocate the volume and weight of the engine in parametric sizing. Additionally, propulsion is tasked with identifying various RBCC specific impulse profiles for which will be outputted for trajectory and performance for their weight ratio calculations. Next slide.
In trying to accomplish this, we took data from literature research from past RBCC engines, including engine schematics, as well as past specific impulse profiles. We then compiled that data and output it to synthesis and trajectory and performance. Next slide. Our inputs were mainly from literature research. We performed like a slide analysis determining the weight and the volume of the engine. We also compiled 3 different fueled RBCC specific impulse profiles so the trajectory and performance could trade fuel types in the convergence logic. Next slide. We used 2 different engine schematics for our synthesis outputs for engine thrust to weight and volume coefficient, which were both used to determine which one would give us better results. And then the ISP profiles were compiled and set the trajectory and performance.
In parametric sizing, an initial constraint analysis must be conducted in order to determine the thrust required for takeoff, climb, and landing. And this is done utilizing Rossing's methodology. Next slide, please. As you can see, this is a simplified breakdown of our process where we calculate thrust for takeoff and landing, taking into account one engine and operator scenarios. And this is then output to synthesis so they may size the engine. Next slide.
The other responsibility of TMP and parametric sizing is to determine the amount of fuel needed to complete the mission. A typical low Earth orbit mission will typically travel at around Mach 28, which is 28 times the speed of sound, or roughly 17,500 miles per hour, which is just a hair faster than your average 2006 Volkswagen Jetta. And unfortunately for us, there are no gas stations in space. And so you have to take all the fuel you need to complete the entire mission with you in one go. As such, it's imperative to optimize fuel efficiency and fuel budgeting in a holistic manner of the vehicle synthesis. Next slide. So you can see here we started with generating a plausible trajectory for the vehicle in order to further our analysis. We did this by looking at prior studies and taking that data and using that to generate a parametric trajectory. Next slide. Here you can see the results of that. This was used to determine state matrices, which were used in the next part, next slide, to calculate the weight ratio using a modified version of Breguet's equations, which have been used for aerospace vehicle design for over 100 years. Next slide. So you can see here, this is just a result from the solution space. You can see we traded hydrogen, methane, and a mix of hydrogen and methane. And by far the most efficient one in terms of weight ratio was hydrogen. Methane was much higher, and then the mixed one was actually one of the worst ones, because although the weight ratio is a bit better, it's much more voluminous. And that brings us to the trade study of the vehicle solution space as a whole.
So for the trade studies, we did 2 trade studies, the propulsion fuel and the crew number. The propulsion fuel, as Scott talked about, was hydrogen, methane, and a mix of the both. And we went with hydrogen just because of the amount of takeoff gross weight it lowered in our solution space, along with the recommendation for propulsion. For crew number, we studied the effects of crew number to see how much it varied takeoff gross weight, and it varied significantly. However, because we are limited to our mission, we initially used 7 members for crew member and eventually changed to 8. With this, our results are as shown for the 30 kilopound and 50 kilopound, and we chose a point based off the best combination of wing loading, tau, which is the slenderness of the vehicle, and the takeoff gross weight. We will now take this into configuration layout as seen. In configuration layout, this is our main MDA, which is essentially split into base model generation, external layout, internal layout, and then control surfaces. Doing it in this way allows us to build up the vehicle from the bottom up to have a feasible vehicle. This is an overview of how we do it. We take that design point and build a base model using geometry analysis, and then using this multidisciplinary analysis and comprehension, we then create an internal and external layout to then be evaluated in configuration evaluation.
Geometry will be at the forefront of the CL design phase, as we will incorporate all of the inputs from the design inputs from every discipline. Next slide, please. We will start off with
The number seen over there can deal with structural, aerothermal, and aerodynamic concerns at the same time. You can see that we went through a bunch of revisions over here, and basically we ended up increasing the thickness and making it thicker and thicker until we made room for the landing gear at the end. So yeah, next slide.
Alright, in configuration and layout, weight to structure's main objective is to determine the internal and the external components weights. And this will give us a CG location and then the forward and aft CG limit as well, to ensure that the aircraft is stable throughout the flight, which will be given for stability and control and aerodynamics as well. Next slide. So this is our weight estimation methodology. We analyzed like 5 different methods where it was verified, and we used certain weight estimation techniques from different methods that had the lowest percent error as well. Next slide. So our pax count and cabin weight estimation was determined through a constraint analysis to determine the max pax count. So we can sell the most tickets and make the most money, right? So we determine the weight of the passenger, and then through process safety and FAR regulation as well, determine the baggage weight, the environmental control and life support, as well as furnishing weight, and this determined the total pax count. Next slide. So here's our percent error and weight estimation techniques results. It should be noted that all of these methods could be overestimated or underestimated depending on the vehicle's configuration and the estimation used as well. Next slide. And here are our results. As you can see, for the 30 kilogram, the structural components weight, the majority of it is the fuselage, and then for the propulsion components weight, the fuel and the tanks as well. The main one is the liquid oxidizer because it's the most dense one there. And then for the systems and equipment weight, these are all the internal one. The main landing gear, because our vehicle is a single stage orbit, horizontal takeoff, horizontal landing, the main landing gear has to support enough weight, and therefore it had to be made out of strong material as well. And then for the payload cabin weight, there's the distribution, and that's our total weight for the 30 kilo-pound configuration, and then also 50 kilo-pound configuration. And our max pax count is 52, and 88 for 30 and 50 kilo-pounds each. Next slide. So this is our initial landing gear analysis. We looked at different vehicles with similar geometry, takeoff gross weight, as well as mission requirements to get an initial idea for the landing gear geometry and placement, the wheel track, wheelbase, as well as CG. And this gave us and the one we chose was the beautiful triple twin tandem. And these were the one based on the amount of volume constraint and placement constraint as well. And then we determined the initial height based on the open VSP to get a clearance angle. And this, with the weight reduction technology that we implemented, we went with a low development risk, which was pretty moderate. And then for 0.80 for the nose one, we want to go high because the main one needs to hold the most load. Next slide.
So in CL, it's important to create an internal and external structural layout because it's the skeleton of the vehicle and it supports it. So the process to do that is shown above, and took inputs from geometry and empirical data. Next slide, please. So the layout for the 30 kilopound model is shown up here. The red rectangles are representing the empty space for the landing gear to go in and out of. Now I want to compare it to the 50 kilopound model for you. Next slide. So since the 50 kilopound model is a lot heavier and it's bigger, it requires more support and therefore more structural material. So to account for this, we added 1 to 2 members in each place. Next slide. Now for the TPS and material selection, it's a similar process, except the outputs were the sum of the mass and volume of the TPS, material thicknesses and choices. So the table over there on the left shows how the more expensive and stronger materials are safe for the more critical areas. And then the table on the right here shows the outputs of the thicknesses for each TPS material. Next slide, please. And it's important to note that SSTO vehicles can go through 7 times greater heat flux than traditional reentry vehicles. So we need to use advanced composites and alloys in our design. And we did that by using titanium aluminide in our internal components, since it has a very high thermal resistance and it's slightly lighter than traditional titanium.
All right, so here is our components placement. We did research and we determined that we want to create a very central CG to add CG location, and we modeled it, and these are our CG limits. As you can see, that will be given to stability and control next slide. All right, so these are the internal components, the location as well as the external weight implemented to get the CG location from OpenVSV for the 30 kilopound and the 50 kilopound CG limit. Next slide.
During the configuration layout phase, the stability control discipline will be in charge of defining the initial sizing and location of the stability control components, and later reiterating it through the configuration evaluation through high fidelity analysis. Next slide. So it's done by using empirical data in the form of volume coefficients, building a vehicle database, and calculating the volume coefficients, taking the average of it. Next slide, please. This is the initial configuration of the canards and vertical tails using the volume coefficients. Next slide.
Configuration layout, stability and control will also be determining an initial layout of the RCS systems, which are the thrusters used for attitude control in space as well as re-entry control. Next slide. We based our placement off of the space shuttle because they have a similar size and they're going to be needing the same amount of control authority as the space shuttles did. So we have a non-dimensionalized length where they're going to be placed, and we're going to apply that to our vehicle. Next slide.
So with all that analysis, we then have these 2 configurations, our 50 kilopound configuration and 50 kilopound configuration. It should be noted that while we only have 2 configurations here, it has dual purpose where it can hold both cargo in the payload or packs, which is why we studied both. And now we move on to configuration evaluation. Configuration evaluation, here's our MDA to do the process. Essentially what we do is a high fidelity analysis of the vehicle. So we can split into 5 different phases: takeoff, ascent, orbital, maneuvers, reentry and glide, and landing. And we use this in conjunction with mission requirements to then conduct high fidelity disciplinary analysis to understand if the vehicle can meet all mission requirements. And if it doesn't, then we will move back to CL and refine the vehicle. Or if it does meet all the constraints, then we have a finalized vehicle configuration.
In configuration evaluation, Aero is responsible for determining the aerodynamic performance of the vehicle and as well as performing an aerothermal analysis. The aerothermal analysis was given the trajectory and performance to be able to modify the trajectory for both the ascent and descent, as well as help with the TPS selection. The aerodynamic performance was given to the wide variety of the disciplines who needed it to calculate anything that needed. Next slide.
In CE, Aero will determine the lift and drag coefficient of the vehicle through all flight phases, which will, as he said, determine the aerodynamic capability of the vehicle to perform all flight phases as well as the missions. The CLTV will be verified using the same tube as they provide liquid data to be compared to the vehicle.
Aerodynamics has many different methodologies, and from these different methodologies, we can get all of these like assumptions, like cold wall assumptions, and we can also get stagnation point heat from like set frames. Sweep effects also help, and then physical geometric considerations from the weighting intensity methodology ultimately helped us to choose that. Next slide. During the ascent, we basically gave TMP a constraint, which was from Nikolai's and second grade methodology. You can see right over here. Next slide. During descent, we can see that the velocity graph over here, as a function of altitude, is up and down, it's kind of squiggly. So it reacts, the temperature reacts to that because of the fact that it's very dependent on velocity and the nose radius and also density of the atmosphere.
During the configuration evaluation phase, the aerodynamics discipline was required to provide outputs to the stability control discipline for their static stability analysis. One of these parameters was the component lifts. It was found using DSP Aero and, for subsonic and low bump regimes, and found using total lift ratios using literature search. Next slide. Similarly, the elevon deflection lift was required to be outputted to the stability control discipline. This was found through doing using empirical data from a study of a geometrically similar vehicle and taking the percentage increase in lift average and using it and outputting it to stability control. Next slide, please. Now with all the aerodynamics inputs, we can now start the statistical analysis. Next slide. This was started by taking inputs from aerodynamics, geometry, and trajectory and performance. Next slide, please, and outputting these stability control characteristics. The first analysis is the landing analysis, and it can be seen that all axes are stable, and this could be attributed to the components chosen in project initiation. Next slide. Similarly, the descent is stable in all phases as well, all along axes, and this could be attributed to reiterations in the fuselage, wing, as well as the stability control components. Next slide. Here we start seeing instability in the directional axes, and this instability is very small and could be fixed using control deflection. Next slide. Similarly, for the landing, the pitch and the yaw stability are a little unstable, but similarly to the descent, it could be fixed using controls as well as reiterating the components. Next slide. So what did this all do? This reiterated the canards and vertical tail, and all of the reiterations weren't necessary because stability control requirements not being met, but could also be attributed to multidisciplinary requirements not being met. Next slide. And future plans for the stability control discipline to analyze the reaction control system, to do orbital maneuvers, control analysis in order to investigate emergency scenarios, and further stability analysis to minimize drag and maximize lift through trajectory enhancements.
All right, so configuration evaluation, our main goal is to get a CG target and optimize it for a better aerodynamic performance and more based on stability requirement as well. And we will also do a structural load analysis for the landing gear and then the wing. Next slide. All right, so these are our landing gear finalized placement. We're gonna look at the overturn angle, clearance angle, tip back angle to make sure that the vehicle would be stable throughout during taxi and takeoff, and it would consider all the FAR regulation as well. Next slide. So here is the results from our clearance, overturn, and wheelbase and track, and the different loads. The brake would the main landing gear will have the braking system, so we have to consider dynamic loads as well as the acceleration loads upon takeoff. So it needs to withstand the extreme amount of load. Next slide. Okay, so here is our design for the main landing gear. Based on the load per tire, the tires that could only withstand this much load was the space shuttle tire. It could handle up to 100 to 160,000 pound force, and that's what we're going to use for the nose and the main landing gear as well. Next slide. So here's a model of the nose and main landing gear. Due to our very constrained space for the main landing gear, we had to use inspiration from the XB70's main landing gear for the triple tandem, where it could rotate and fold into the wing compartment as the wing was low mounted and the propulsion system was right underneath the belly. All right, thank you.
So in configuration evaluation, weights and structures also focuses on refining and testing the structural layout. And what I mean by that is changing the amount of material and its placement so it better fits the requirements of other disciplines. One example of this was how those frames over there shown by the arrows had to be moved because they were initially conflicting with the location of things like the propellant tanks or the cabin. So every time the layout's changed, it has to be tested to see if it can withstand the maximum shear stresses and bending moments. Next slide, please.
In configuration evaluation, propulsion job was developed to develop processes for calculating the thrust and the fuel efficiency of the engine over the entire descent. We also performed an inlet sizing analysis to determine what kind of shock angle, what kind of deflection angles would be best most effective for the engine during high speeds. Next slide. We took 5 different analysis methods for each rocket mode, for each engine mode, and ran them through the trajectory, output from trajectory performance and parametric sizing to determine a preliminary thrust and fuel efficiency profile. These processes were also output to trajectory performance. Next slide. We had 5 different processes to do this. Next slide. These include the full rocket takeoff analysis and the air augmented rocket analysis, where we measure the 2 flows coming into the engine to determine the thrust, and ramjet and scramjet analysis, where we use a stream thrust analysis, along with the oblique shock relations to determine the thrust and fuel efficiency, and the full rocket analysis. Next slide. Here you can see at point 1, our rocket has a lot of throttle ability, so that if we need to decrease the thrust, we can also decrease the amount of fuel we're using. At point number 2 are our maximum temperatures, which will need to be minimized by changing our fuel-to-air ratios. Our maximum thrust is seen at point 4, which is our transition point in our air-augmented rocket mode, which is good because there's a lot of drag there at lower altitudes. And points number 3 are our scramjet and ramjet, where we have the lowest amount of fuel usage. Those modes will need to be maximized the time that we're using them so that we can use the least amount of fuel. Next slide.
As we saw in the previous analysis, safety was in accordance with 425 and CFR. Another analysis we must conduct is a cost analysis of our vehicle, where we determine development, production, operation, and per flight costs. And this is done utilizing TransCost 8.2. Next slide, please. This is our process. The inputs that we require are the various weights of the vehicle, and with these we can use the cost estimation relations to determine the cost of our vehicle. And this is done with the 50 kilopound and 30 kilopound configurations. Next slide. And as you can see, this is a simplified breakdown of our process where we determine these respective costs. Next slide. And these are results. As you can see, our development cost, which is the cost to develop our vehicle, for both configurations, about $30 billion. The reason why the cost of this vehicle is so high is due to the fact the single stage to orbit vehicles are so complex, plus we have a large amount of mass. We're about 5 times heavier than the X30. And the recurring cost or production cost is what we have to produce, or the cost to produce our vehicle. Next slide. And these are operations costs as well as our per flight costs. Operations costs, we have about $100 million for each configuration, and our price per kilogram for ranges from $10,000 to $20,000, and our ticket prices for each are about $5 to $6 million per passenger. Next slide. And the reason why our ticket costs are so high is due to the fact that as cost stays between each team, we assume that we're only producing 1 unit or 1 vehicle. In order to decrease our costs, we assume, or we conducted a trade study for increasing our units. So, as you can see, we can reduce our ticket count or ticket price from about $6 million to $300,000, meaning that we logarithmically decrease our costs as we increase our production. And this, as you can see, for this current mission that we have, for only doing 1 unit is unfeasible for this mission. However, if we increase our production, we can be feasible and rival Blue Origin. Next slide.
One second. I just wanted to emphasize that what he said. This is a logarithmic scale, meaning that as the payload increases and as the amount of passengers increases, the price is actually decreasing by an order of magnitude. That's 10 times cheaper, not just the 2 times. It's plotted like this for convenience, so you can see such a large data set.
Geometry is responsible with 3D printing a finalized configuration. Displayed here is a 1/65 scale model of our latest configuration, and here is a build-up process of our configurations. Next slide.
Right. So, in configuration evaluation, trajectory and performance is tasked with providing a overall simulation and trajectory analysis to provide both the opportunity for other disciplines' inputs to be properly accounted for, and also for the trajectory and performance to be able to give outputs back to the disciplines so they can perform their analyses. We did this using multiple different methodologies. We used a Roscoe methodology for takeoff and landing. We used a specific excess power optimization for the main ascent, and we used a specific energy optimization for the descent from Cranfield University. Next slide, please. So as you can see here, this is the results for the takeoff. You can see we just did a simulation of it, and we found that we could get to the speed well within the end of the runway at Cape Canaveral. Next slide, please. And this stage is the most critical phase because this is where the vast majority of our fuel is burned. And so you can see we performed a specific excess power optimization in order to calculate the amount of fuel needed. And what that means really simply is just that you need to be going fast to get into space. And to go fast, you need more energy. So this is a way to optimize what is the cheapest way in terms of fuel to add that energy into the system. Next slide, please. So you can see here on descent, it's a similar thing, but this time we're trying to slow down. And we use the atmosphere this time to our advantage to implement the drag and be able to slow down without expending fuel. Next slide. As you can see here, the next step in configuration evaluation was to converge again. So what we did is we took the outputs from all the disciplines, from aero and propulsion, weights and balance, geometry, and we used that to reconverge on our solution space. And in doing so, we found an interesting trend. Next slide, please. You can see here that we vastly increased our weight due to a small decrease in performance in the high supersonic to low hypersonic regime. That increased fuel required more fuel to bring it up, which required more volume to keep that fuel. And the nature of these vehicles means that that had a massive impact on our overall vehicle size. And so in the future, we're planning on finding ways to optimize aerodynamics in that region so that we can maintain our low weight and our low weight ratio.
So I just want to showcase our timeline again. We're constantly working on our CE analysis right now and making sure we can get our deliverables as our final report is due on the 9th of August. Are there any questions?
Thank you so much.